So in this question we have two spheres A and B. Sphere A is moving at a speed of 0.6 meters per second at an angle, let's say, of theta to the horizontal, the I-axis. Sphere B originally is at rest and so has a speed of 0I plus 0J. As a result of the collision, sphere A is going to move at a right angle to its original direction of motion. So what we're going to do is, because we know that all of this is 90 degrees, we're going to call this section of it in here 90 minus theta. So theta being the original direction of motion, and then afterwards the velocity vector of A makes an angle of 90 minus theta with the horizontal. What we're going to do is we're going to write down the speed of A as a resolved vector in terms of its I and its j components. So we can see that it has an I component, or an I speed, of 0.6 cos theta, and it has a j component of 0.6 sine theta. So writing that down, u of A is equal to 0.6 cos theta I plus 0.6 sine theta j. We're told that after the collision the speed is 0.2, and if we resolve the velocity vector afterwards, we can write that as that the velocity of A is equal to minus 0.2 cos 90 minus theta I plus 0.2 sine 90 minus theta. So we're expressing the angle in terms of theta, as we know that the direction of motion afterwards was 90 degrees. And the I component is a minus, as we can see from the sketch that it's moving to the left, to the opposite direction. Now, using rules from trigonometry, we know that the cos of 90 minus theta is actually the sine of theta, and the sine of 90 minus theta is actually the cos of theta. Because the collision took place where the line of centers was along the I-axis, we know that only the I component changes as a result of the collision. So I've colored the j component in green to show that these are actually equal to each other. The j component was the same before and after the collision. So 0.6 sine theta is equal to 0.2 cos theta. I'm going to divide both sides by cos theta and divide both sides by 0.6 to give me that sine theta over cos theta is equal to 0.2 over 0.6. Sine theta over cos theta is equal to tan theta, and 0.2 over 0.6 is equal to 1 over 3. To find the angle, I find the tan inverse of 1 over 3, which is 18.43 degrees. So we can see that afterwards the direction of motion is west, 18.43 degrees north. Now, just to have it ready for future parts of the question, I'm just going to do a model triangle with tan theta is equal to 1 over 3, and that will yield that cos theta is 3 over root 10 and sine theta is 1 over root 10. If we want to just check that, we just draw a little triangle where the opposite side is 1 and the adjacent side is 3. And then if we do Pythagoras theorem, we get that the hypotenuse is equal to the root of 1 squared plus 3 squared, which is equal to the root of 10. So we have that the cos theta is equal to the adjacent over the hypotenuse, 3 over root 10, and sine theta is equal to the opposite over the hypotenuse, 1 over root 10. So part 2 of the question asks me to find the coefficient of restitution E. So I'm going to use the PCM and the NEL. I'm going to only use them in the I direction, as the collision took place where the line of centers was along the I-axis. It's only the I component of the velocities that changes. The j component of the velocities remains the same. So subbing into the formula, the masses, m1 is equal to m and m2 is equal to 2m. I get that m times 0.6 cos theta, the velocity in the I direction of sphere A before the collision, plus 2m times 0, the velocity of sphere B in the I direction before the collision, equals m by minus 0.2 sine theta, the velocity in the I direction of sphere A after the collision, plus 2m times v2, v2 the unknown speed of sphere B in the I direction after the collision. I'm going to replace cos theta with 3 over root 10 and sine theta with 1 over root 10, which I found using the model triangle in the previous question. And then I'm going to divide across by m to give me that 9 root 10 over 50 is equal to minus root 10 over 50 plus 2v2. I'm going to add a root 10 over 50 to both sides to give me that 2v2 is equal to root 10 over 5, and I'm going to divide both sides by 2 to give me that v2 is equal to root 10 over 10, meters per second, and that's the speed in the I direction of sphere B after the collision. Using the NEL, I have that V1 minus V2 is equal to minus E on U1 minus U2. V1 is the speed after the collision in the I direction for sphere A, which we have as minus 0.2 sine theta, but we tidied up to give us minus root 10 over 50. Minus V2, which is root 10 over 10, which we found in the previous part of the question using the PCM, equals minus E. E is the variable we are trying to solve for. On U1, the speed in the I direction before the collision, which was 9 root 10 over 50, minus 0, the speed of B in the I direction before the collision. Tidying this up, I have that minus 6 root 10 over 25 is equal to minus E on 9 root 10 over 50. And then dividing both sides by minus 9 root 10 over 50, I get that E is equal to 2/3. So the third part of the question asks us to find the loss of kinetic energy. It actually tells us that it's 0.06 m. So I'm going to take the velocities in the I direction only, as the velocities in the J direction remained unchanged. So the energy before is half m1 u1 squared plus half m2 u2 squared, where m1 and m2 are the masses respectively of sphere A and B, and u1 and u2 are the speeds before the collision in the I directions of A and B. So subbing those into the formula, I have a half on m on 9 root 10 over 50 squared plus a half by 2m by 0 squared. Remember, initially sphere B was at rest. And then squaring 9 root 10 over 50 and multiplying that by a half, I get that the energy before in the I direction was 0.162 m. For the energy afterwards, I have a half m1 v1 squared plus a half m2 v2 squared. Again, m1 and m2 are the masses of the two spheres, and v1 and v2 are the speeds in the I direction after the collision. So subbing those into the formula, I have half on m on minus root 10 over 50 all to be squared, plus a half on 2m on root 10 over 10 all to be squared. Tidying this up, I have m over 500 plus m over 10, and adding these together, I get 51m over 500, or 0.102 m. To find the loss in kinetic energy, then I just subtract the energy afterwards from the energy before, and I get 0.06 m, which I was told was the loss in the question. Just to show that we would have got exactly the same loss in kinetic energy had we taken the magnitudes of the velocities instead of just the velocities in the I directions, I found the overall magnitude of the velocity of A after the collision, which was 1 over 5, and I already have the magnitude of sphere B as it's only moving in the I direction. So the energy before then becomes 0.18 m, and the energy afterwards becomes 0.12 m, and then subtracting these, I get a loss of kinetic energy of 0.6 m. So the same answer as we got in the previous part.